Go beyond limits with an oscilloscope built to take you there. The Tektronix 5 Series B MSO has an award-winning interface that enables you to effortlessly see and measure even the smallest signal detail. With up to 8 analog or 64 digital channels, plus an additional auxiliary trigger input, you won't be limited by your number of inputs. Go beyond the time domain with built-in spectrum analysis. Choose between an embedded operating system or Windows, and go beyond your lab with powerful off-scope analysis that gives you the freedom to work from anywhere, anytime. Go beyond limits and turn your big ideas into reality. Visit tech.com/5 Series MSO.
Hi, I'm Wilson Lee, Market Segment Lead for Education at Tektronix. We're here today on the Oregon State University campus working with the global Formula Racing team to show our latest product innovation. Let's go see what they have to say. You are the first outside the product line R&D bubble to have a look. We're ready for the reveal.
Definitely my first thought was how much different it looked. It looked much more modern. I definitely talked about how cool it looks and the functionality of it, how easy it looks to be able to take around and use.
It was just so modern. It looked so much easier to use. You walk into class, freshman, sophomore, and you have no idea what all these knobs and buttons do. The new product is so intuitive.
I did think it was a vast improvement.
When I first saw this, I was really surprised with the fresh look of the device. All controllers now are more user-friendly.
Futuristic, just because that's kind of the impression I got during the reveal. It's something that you can see yourself using now and in the future.
Really intuitive and modern, easy to use. Could really be a game changer for many students.
Hello everyone, welcome to Tektronix Innovation Forum, and in this session we will talk about wideband applications and validation test challenges. My name is Yogesh Pai and I'm product manager for power solutions at Tektronix, and in this session I'm being joined by Sri Krishna, who is our senior technologist for power solutions. Let's get started. Here is the agenda for today's presentation. We will start with the understanding of wideband technology, a typical test workflow, talk about some of the test challenges and potential solution to address some of those test challenges. Let's start with the basic question. What is wideband and why are we talking about it these days? All traditional power electronic designs have historically been based on silicon technology. Compared to these traditional silicon power devices, wideband power semiconductors like silicon carbide and gallium nitride have special characteristics. These characteristics translate into clarity when we investigate the device specifications. Given the same die size and thickness, the wideband devices can provide higher breakdown voltage, higher current, higher operating temperature, and most importantly, offer faster speeds and lower switching losses compared to silicon devices. All these characteristics translates into higher energy efficiency at a reduced form factor, making it an ideal choice for the designers. As the adoption of wideband devices is increasing, the cost of manufacturing and integrating them into traditional silicon designs is reducing day by day, making it a win-win situation both for the designers and the consumers. Because of these advantages, the wideband devices have been named as a key enabler to revolutionize power conversion in the recent years, and they are available in the market both as discrete devices and power modules. Silicon carbide and gallium nitride are two of the most popular wideband technology devices available in the market today. There are several design considerations that are required before adopting the wideband technology in the silicon designs. Some of these key design considerations include choosing a robust reverse recovery diode in the designs, choosing components such that we have near lossless switching parameters, operating at the highest switching frequencies and high temperatures, exploring newer topologies to help achieve higher performance in various SMPS designs, and optimize designs that can help go to market faster. Choosing correct wideband-gap devices like SiC MOSFETs or GaN FETs for different applications depends on the operating voltage levels and switching speeds. SiC devices are most suited for medium to high voltages, typically over and above 1.2 kilovolt range. This includes application like transportation, wind energy, and power grids. GaN devices are most suited for lower voltages, typically in the range of 600 volts or less. This includes applications like consumer electronics, power supplies, chargers, and UPS. And in the range between 600 volt and 1.2 kilovolt, that is where both SiC and GaN have equal play based on the application needs. This area includes applications like solar inverters and EV, HEV inverters and motor drives. The adoption of wideband gap in the green power segment promises sustainability and diversifying the energy supplies, while its adoption in the automotive segment promises to reduce carbon footprint and conserve fossil fuel. So what are some of the high-level test challenges? Devices based on silicon carbide and gallium nitride can switch at much higher frequencies and also have far lower leakage compared to silicon. This also means that there is a need for sourcing higher voltages in testing, and there is also a need for greater current measurement sensitivity. It can be quite challenging to characterize these new devices at very low levels of current. The instrumentation used must be capable of characterizing significantly higher rated voltages and peak currents than even before, while providing the measurement resolution and accuracy characterizing these new material devices. Here we have a typical power converter workflow. For example, this could be an EV inverter workflow. The workflow starts with component characterization on the left, then goes into the simulation block in the center, and finally ends with the validation block on the right. The characterization block is particularly focused on testing wideband gap components such as MOSFETs, IGBTs, both in its discrete and module forms. An engineer working in this block is interested to define the test limits, characterize the components across various operating frequencies and temperature range. This is also sometimes referred to as static characterization. This helps the engineer to publish the device models and component data sheet, which can then be referred to build application reference designs and later an entire inverter system. Next, we have the simulation block. Here, the engineers integrate the components into the designs and create a SPICE model. As the designs solidify, the engineers work on creating and simulating an entire inverter performance. As you know, the cost of producing an actual hardware and testing is quite high. So ensuring we have captured the right test data and covered all the test cases to evaluate the performance at simulation stage becomes critical. Finally, we have the validation block. Here, the engineers are working on some early reference designs and end systems. This is where components that were characterized at the first stage get integrated. Some of the common focus areas include gate driver reference designs, designing for highest efficiency, debugging failure, and publishing the reference design documentation. And for system engineers, it's more around trying to reduce the board size, gaining access to the test signals, and meeting the OEM's requirements. Let us now talk about typical test challenges in the characterization and the validation blocks. First, we shall talk briefly around the test challenges during the characterization stage, although this presentation will focus mainly on the validation testing areas in detail. When testing at high voltage levels, safety is of utmost concern. Some SMUs can source voltage up to 3 kilovolt, so precautions must be taken to ensure that the operator is not exposed to unsafe voltages. Tektronix offers special cables which are fully rated for use at 3 kilovolt that the test system designer can use to interface to the device under test. The newer SMUs provide a rear panel safety interlock connection so that the high voltage output is reduced to a safe level if the interlock is not engaged. Finally, if you are working around high voltages, make sure that you are using proper safety gloves so that you don't come in direct contact with energized components or circuits. When it comes to selecting instruments for high power, it's recommended to use instruments like source measure units, SMUs. These instruments provide integrated measurements, precise control, and a simple 4-quadrant operation where the SMU can source or sync precise voltage and current signals. When designing the GaN or SiC FET devices, the main characteristic is to measure the family of curves. This measurement can easily be performed using the source measure units and a software that can control the SMUs and graph the curves. On the screen, you will see one such image of the curves performed using the Keithley dual channel SMUs and the Kickstart software. An instrument such as a parametric analyzer is also used quickly to get parametric insights, perform fast and clear, accurate IV characterization across different operating frequency range. Tektronix had recently hosted an informative webinar that highlights key test challenges around the SiC and GaN component testing with an emphasis on the 5 key measurements that are shown here. This webinar is available on demand, and we have added a link to that webinar on this slide, which will be available as part of the handouts, and you can check out that webinar offline. With that, I would like to hand over the rest of the presentation to Krishna to talk about characterization testing, validation testing, test challenges, and some potential solutions. Over to you, Krishna.
Thanks, Yogesh. We'll see about SiC and GaN components characterization. As you know, a MOSFET is a voltage control device, which means it operates as a switch based on the threshold voltage applied to its gate terminal. Some of the important parameters for MOSFET characterization are measuring the gate voltage and drain current. Observe the right hand on the screen, which talks about the wafer and package level and also the key parameters to measure. First key parameter is RDS on, which is the on-state resistance. It should be as low as it could be to minimize the conduction losses. As RDS on is small, it requires high current capability to measure this parameter. The second key parameter is gate charge. This must be as low as possible to minimize switching losses. It's a critical parameter for switching performance and gate drive circuit design. It's also important to estimate the switching loss parameter. The 5 key tests which are important for characterization are IV drain curves, on resistance, that's RDS on, leakage current, breakdown voltage, and gate charge. We are not going to discuss these things in detail. Please refer what Yogesh had shared in the previous slide, the webinar link, for more details. Next, we will talk about the system validation and the test challenges associated with it. In the characterization stage, mostly discrete components get characterized as per the datasheet values. The challenge comes when these components gets into circuit and ready for use in a particular application. This application, the application board design needs to be tested for different blocks within a circuit operation. It is very critical that board parameters are within the characterized values. Some of the biggest challenges working with SiC and GaN devices are the gate drive requirements. SiC requires much higher voltage, higher gate voltage with a negative bias for turn-off. On the other hand, GaN has requires a much lower threshold voltage, requiring tight gate drive designs. Wideband-gap devices, by the nature of their physics, also have a higher body diode voltage drop that requires much tighter control of dead time and turn-on, turn-off transitions. Devices based on wideband-gap materials are able to switch at much higher frequencies than conventional silicon versions. They also tend to have much lower leakage currents. As a result, to properly characterize the wideband-gap semiconductors, testing requires at higher voltages and more sensitive measurement of currents. Solving these challenges may be tough for the power designers. It's critical that you have an accurate electrical source and measure testing when characterizing these high voltage devices so that the right decisions can be made in a timely fashion. Generally, discrete components are tested within a temperature chamber and range of voltage and currents. So safety becomes very important to test worst case voltage and current, and is very important during applying of high input voltages. Many times probing access is a challenge, especially putting loops for the current probe access. It is recommended to use shunt resistor approach to reduce the parasitics because of the loops. The other challenges are floating challenges. Devices are not grounded, and grounding through the scope would cause failures. Common mode interference from switching completely distorts the measurement. What designers want to see are control signals on switch mode power supplies and current measurements across shunt resistors. So IsoVu Probe enables differential measurements on floating side with faster signals as low as 1 nanosecond. The IsoVu Probe has fantastic accessories to solve the probing and connectivity challenges. Now let's look at the typical test system for doing the measurements. Typical equipment setup for Wpg measurements, you can see an illustration on the right side. It needs a AFG 31000, that's the external signal generator to generate the stimulus. This connects to the isolated gate driver and uses the double pulse test application on the AFG to quickly generate the pulses with varying pulse widths. The isolated gate driver is what turns the MOSFET on. Another important piece of the test setup is oscilloscope. This is very essential for debug and analysis. The setup uses Tektronix 5 or 6 series MSO. This is used to capture and measure various drain to source voltage, gate to source voltage, and drain currents. Typical characteristic of an oscilloscope that are essential are: it is very important to have high ADC resolution. 12-bit ADC support can go higher with, usually it's 12-bit, it can go higher with high-res acquisition mode. This is very important because small details on large signals requires high resolution. MSO 6B series is a best-in-class noise sensitivity. The 12-bit analog to digital converter delivers 16 times the resolution of conventional 8-bit ADC. So in summary, high-res mode delivers up to 16 bits of vertical resolution for finer view of low-frequency signals. Another capable tool is off-scope analysis. We offer PC-based TechScope software, which lets you to analyze outside the scope. This will let you use the scope hardware for critical analysis and do the post-analysis on the software. It is very important to optimize signal-to-noise ratio. In all measurement systems, especially in digital devices such as modern oscilloscope, good measurement technique requires keeping signals as large as possible without clipping to minimize the effects of noise and to maximize vertical resolution. Then coming to the probes, that's the essential piece of the connectivity. The IsoVu Probe typically has a very high common mode rejection ratio. This probe is recommended to be used to measure gate to source voltage, specifically for wide-bandgap semiconductors, since it also offers high bandwidth, high common mode voltage. We will see some more details in the next upcoming slide. And finally, we also need a DC power supply or a source measure unit instrument to supply the load voltage. And we also need a good set of automated software measurements to do large set of analysis with minimal error and lesser time. We will see more details about this in the upcoming slides. Let's look at some more details about the IsoVu probes. IsoVu technology is the only differential probing system for wide-bandgap testing. Some of the important attributes of this probe, which makes it suitable for wide-bandgap measurements, are having high CMRR, high bandwidth up to 1 GHz with less than 350 picosecond rise time, supporting up to 60 kV common mode, and having a wide input range up to 2500 volts. Why IsoVu Probe? Please note some of the probing challenges for wide-bandgap measurements is interaction between the high and low side of the power devices. Violation of any specifications or designs can lead to simultaneous conduction, and it blows up the device. It degrades the device, increases switching loss, and also the efficiency of the system. Question to ask is, does your wide-bandgap measurements match your expected results? IsoVu gives you an accurate, repeatable measurement, providing meaningful correlation with expected performance. IsoVu rejects common mode interference, so you can see the true differential signal. CMRR is a critical but often overlooked specification. For example, can a 5-volt differential signal be measured in the presence of 100-volt common mode signal? Yes, with IsoVu probes it is. When we want to characterize entire wideband gap switching circuit, it's important to look at the characterizing key parameters such as gate voltage, drain to source voltage, and drain and source currents. Characterize the time alignment of high and low side events. Optimize and fine-tune switching characteristics such as edge rates, overshoot, ringing, and dead time. So in summary, combination of IsoVu Probe with Tektronix 5 or 6 series MS Probe ensures effective technique to debug and fine-tune WBG designs. Let's look at key measurements for system validation. WBG electrical measurements are governed by JEDEC and IEC standards. JEDEC committee JC70 wideband gap power electronic conversion was formed in 2017. It has two subcommittees, JC70.1 and JC70.2, catering to GaN and SiC power devices. We are part of JEDEC work group, and Tektronix is an active participant and contributor to this group. Next, let's look at some of the scope-based power solution, what we offer. It talks about different measurements catering to the different stages of the power devices, starting from input analysis, then switching analysis parameters, magnetics for the transformers and the inductance, and output analysis, which covers efficiency and ripple measurements. These tests helps to measure different parameters in a single box solution. Some of the other important measurements on the input side are harmonic measurements, which supports various pre-compliance standards such as IEC 61003-2, MIL standard, AM14, and custom limits. Phi-power is a solution on scope, which providing various switching loss parameters, which is very important for WBG measurements, such as energy on, energy off losses, conduction loss, total loss, internal resistance, that's RDS on, rate of change of voltage and current, safe operating area for different flavors like forward and reverse biases, and efficiency measurement. Another important tool which scope provides is spectrum view tool to measure EMI parameters. This is a standard option on most of the scopes. Debugging embedded systems often involves looking for some clues that are hard to discover just by looking at one domain, that is time domain. The ability to look at time and frequency domain simultaneously can offer important insights. Spectrum view enables simultaneous analog and spectrum views with independent controls in each domain. Next, another important set of measurement is double pulse test. It's also called dual pulse test. Double pulse test is a method to measure switching parameters and evaluate the dynamic behavior of power devices. Users of this application typically want to measure the following switching parameters. That's energy on, energy off, reverse recovery parameters with turn on and turn off regions. This is a very important test, typically as part of dynamic testing, and needs an external stimulus using external generator like AFG 31000. And usually switching parameters are analyzed on the first and second pulse. Diode reverse recovery is another class of measurements. There is a reverse recovery loss of the body diode in the MOSFETs to consider. Reverse recovery time of the diode is a measure of the switching speed in the diode and thus affects the switching losses in the converter design. So it's important to measure this reverse recovery. Some of the reverse recovery parameters are TRR, IRR, and QRR, and also rate of change of voltage and current. So this test is performed to guarantee specifications of power devices like MOSFETs and IGBTs. If you look at the different stages of the measurement, it's a cycle of testing going through acquisition of the waveforms using the test setup what we had discussed in the previous slides, analyze through various complex algorithms and measurements, and finally make a report out of these different measurements. As you have seen, there are lots of measurements for system validation. Post-analysis on the acquired waveforms is an important piece to arrive at the key decisions on the designs. From the analysis perspective, building parametric test results over multiple runs and multiple plots, it's very important to get the statistical results, which usually can take days together to conclude the results and arrive at the decisions. A dedicated scope-based validation tool will help a lot to do this analysis with much lesser effort. By utilizing this automated test system, a designer can improve test times, reduce human computational errors, improve repeatability of results, and traceability to which waveform contributed to the failure. And finally, designers can share specific session files to different teams in the organization to further analyze and post-process with much more details. This becomes a powerful tool for the debug and analysis. Thank you, and handing over to Yogesh for further on the summary thoughts.
Thanks, Krishna. Okay, so we have seen that wideband gap technology is clearly the technology of the future. The adoption of this technology requires designers to overcome several significant challenges in testing their power semiconductor devices. Highly sensitive testing equipment, improved test circuit design, and other considerations will be necessary to properly characterize and validate these devices. Tektronix can help you solve these problems related to wideband gap, as wideband gap is one of the focus area for Tektronix when it comes to testing in the power space. So with limited time, we could only cover brief details in this presentation today. However, if you need any further information around wideband gap testing and how Tektronix can help solve your problems, please contact your local Tektronix representative or reach us on tech.com. Thanks for attending this session today.
All right, we're going to talk really quickly about inverter, motor, and drive testing. So what I've got here is an RC car with a DC battery and a three-phase motor inside of it. So in this car, we've got inverters, converters, power rails, a bunch of electronics that are powering this three-phase motor. I'm going to control it with a 2.4 gigahertz controller here. And first, let's just see the car rolling. So that's got a lot of torque to it, right? So the three-phase is being used so that we can deliver a consistent torque to those wheels and the mechanicals. And in the design of an RC car like this, or maybe it's an industrial motor, washer, a dryer, something inside of our electronic vehicles and hybrid vehicles, three-phase power delivery and quality is incredibly important. Doing the testing sometimes can be really hard because you need lots of scope inputs. Here we have 3 differential connections. So you can see at the back of the car, we've made this little test setup with the red and the black differential probes. And then we also have some Rogowski coils to measure the current on 3 phases. So we have phase A, phase B, and phase C. I'm going to get the scope in running mode and give you a little intro to what's on the screen. On the left is a phasor diagram where we can see in red the phase A, B, phase B, blue, phase B, and in yellow is phase C, as well as the DQ0 transform. So that purple circle is the resultant of the DQ0 transform from my measurements on the right half. The top section in yellow, orange, and red is our 3 voltage signals overlaid on top of each other. We can zoom in and see that right here. The next is our 3 current phases, A, B, and C. Again, those Rogowski coils. And then we have the D, the Q, and the DQ0 math being shown below. Let's run this RC car now while the scope is ready to trigger. You can see the acquisition being made here live and the DQ0 updating immediately. And you can see the circle's nice and round, meaning that we've got ideal efficiency when we reach steady state. But when we look at startup, we get a whole bunch of issues with how the 3-phase power is coming on board from that battery. So this would now enable us to zoom in to specific areas and correlate with what is going on in other parts of the system. Maybe we're having an intermittent connection coming from this remote. Maybe we're having issues with our inverters or our converters. And with this scope, we can get down and we can debug each of the small little subcomponents in the system. So we also have the ability to do mechanical measurements on torque and on speed, so we can correlate the power coming from the battery and how that's actually turned into mechanical energy and optimized for losses. So that's just a quick overview of our inverter, motor, and drive analyzer software. This is a solution that works on our 5 Series B MSO and our 6 Series B MSO. Thanks.
All right, thanks everyone for joining today's presentation. My name is Cameron Lowe. I'm a field applications engineer with Tektronix. And today in this kind of brief 30-minute session, we're going to be just going through some best practices when handling our isolated differential probe, also called IsoVu. So I am a pretty heavy user of IsoVu. There's a lot of different customers in the area that I cover that support this product and use it quite heavily. So yeah, we're just going to be going through some of the best practices and things that we've learned along the way in terms of how to use this probe most effectively. Okay, so as a quick kind of agenda coverage, the first thing we'll cover is just some changes and specs on our Gen 2 IsoVu, also called our TIVPX probes. We'll talk about some of the changes that have come in place from our Gen 2, from our Gen 1 probe. Some of you that have used our TIVM or TIVH probes in the past might remember our Generation 1 version of IsoVu. So we'll just talk about some of the changes that come into play with Gen 2. We'll also then get into the best practices. It's going to cover both the operation and handling of probes and their probe tips. And then finally, one area I get questions a lot is, okay, so what other kind of applications outside of wide bandgap semiconductor testing can we use something like IsoVu for? So we'll talk about some of the other areas that I've seen IsoVu used successfully. All right, so first, just again, brief coverage of IsoVu. Those of you attending are probably familiar with the isolated probing portfolio from Tektronix. But IsoVu is kind of the brand name that we use for our isolated differential probes. We released our Generation 1 several years ago and have since come out with Generation 2. The general sense behind IsoVu and where it was originally designed for is for wide bandgap semiconductor testing. Things like gallium nitride, silicon carbide type devices, and some of the challenges that they present, which we'll get into in a little bit later. But in general, IsoVu is best suited in applications where you can make relatively small differential voltage measurements that are in the presence of very, very large common mode. So some of the base specs, we have the best high common mode rejection ratio of any high voltage differential probe in the market, up to 120 dB at DC and 100 dB at 100 megahertz, which is by far and away the best common mode that you're going to find for most differential probes in the market. Coupling along with that, we keep a very high bandwidth with our differential probe. For something as high dynamic range as 2500 kV, you often don't see bandwidths, up above, say, a couple hundred megahertz or so. With IsoVu, we're able to achieve a gigahertz of bandwidth, and where that really allows for some interesting measurements, again, in the wide bandgap space, is being able to really focus in on the DVDT and potentially DIDT type of measurements that are becoming faster and faster in the space of wide bandgap materials. And then I mentioned the wide input dynamic range, and we'll talk about some of the different tips that allow us to get there. So what's important to keep in mind with our Generation 2 probe? So as you can see in the picture in the upper right, we have, this is our new generation probe. Again, the part number is TIVP, and the bandwidth of the probe follows after that in terms of a number. So for example, TIVP1 is a 1 gigahertz probe. So the most notable difference for those of you that have used the Generation 1 of IsoVu is just the size reduction that we've been able to achieve in our Gen 2. So we're at about a fifth of the size of the original TIVH probe family. And the majority of that size reduction comes from the controller box that we were able to completely remove from the signal chain. So now we just have two components, a compensation box that you can see on sort of the left-hand side of the picture, connected through fiber optic cables to the probe head that you see on the right-hand side of the picture, which has a bare SMA style connection which we can connect into different attenuation tips, which we'll discuss later. Apart from just being able to reduce the overall size and mass of the probe, we've been able to improve the gain accuracy of the probe, and we've been able to achieve a flatter frequency response. So for those of you that were operating our Gen 1 probes towards the higher bandwidth range, we've been able to decrease some of the overshoot that was apparent on generation 1 and really flatten it out with generation 2. And then particularly at low volts per division settings, so say below a 1 volt per division, we've been able to improve the noise sensitivity on our generation 2. In addition to that, we'll talk about some of the tips and how that plays into the next slide. We've optimized this particular probe to be used on our kind of newer generation scopes. So our 4, 5, and 6 series MSOs are the scopes that we currently have support for with our generation 2 probe. So let's kind of get into some of the tip changes. So the architecture of the tip, as you might imagine, with the overall reduction in the size of the probe head, required a change in the tips that are designed for it. So our product line team did a great job in redesigning them, slimming them down, making them capable of fitting into smaller, tighter spaces. And to be able to do that, we've also scaled the dynamic range of the probe itself. So you'll see the two different kind of colored bars there illustrate the different probe tips that were required to get to different differential voltage ranges. So we had 7 different tips that were capable of getting all the way out to, or that it made the range capable of our generation 1 IsoVu probe, capable of getting out to 2500 volts kV. And on the second generation probe, the TIVP family, we've extended the bare dynamic range of the probe head itself. So now the probe head, or the SMA connection into the probe tip, into the probe head itself, is now plus or minus 5 volts. And what that allows us to do is actually reduce the amount of attenuation required to get all the way out to 2.5 kV. So you'll see for the generation 2, we now only have 4 different tips available that cover, again, that same differential voltage range as Gen 1. Another important characteristic to keep in mind is one of the changes that we've made with our Gen 2 probe is this adjustment of manual gain ranges. So on the Gen 1 probe, which you'll see on the left-hand side, our TIVH08, you had basically 2 different ranges if you went into manual range mode, a 1x and a 2x range. On the generation 2, we've scaled that range to provide, several different gain ranges to allow you to really dial in as much or as little gain as possible to achieve the kind of differential voltage that you're looking for. So that's really important to keep in mind. Now, one important piece that goes with that is that particular manual range change means that we utilize a particular feature set within the UI of our newer generation scopes. So for that reason, the IsoVu Gen 2 is now supported on just the 4, 5, and 6 series mixed signal oscilloscopes, and it is supported with firmware versions 1.3 and above. So if you're considering, purchasing the Generation 2 or TIVP probe families, first I would, encourage you to check out which scopes you have available at your fingertips and make sure that you have at least a 4, 5, or 6 series mixed signal oscilloscope. And then for those of you that already have one of those scopes, be sure to make sure that you're running some of the latest firmware versions. All right, now let's get into some of the best practices when handling our isolated probe, IsoVu. So one thing to keep in mind, and this is apparent with all active differential probes, but there is a warm-up period that is recommended for any differential probe family. And that allows the different components within the system of that probe to warm up and get to a steady state. That's true of an oscilloscope. That's true of most modern active differential probes, and IsoVu is no different in that regard. Because of the size of IsoVu and the complexity in using fiber optic transmitters and receivers, there is a slightly longer there's a slightly longer temperature warm-up period of 20 minutes that we recommend in our user manual. So be sure to keep that in mind when you're using IsoVu. It does take a little bit of time to warm up. And you'll see the effects of that warm-up period are very apparent from first plug-in. So on the left-hand side, I've got a picture of when I just first attached IsoVu to my scope. You'll see that there's a DC offset, again, apparent with really any differential probe that you plug in that's cold or is at a different ambient temperature from when it was last auto-zeroed. And then after 20 minutes and after running the self-calibration piece built into the scope, sure enough, that DC offset goes away. There's also a warning that comes up if the ambient temperature around the probe changes by plus or minus 5 degrees C. So keep that in mind. We recommend that if the ambient temperature changes by that amount, that you recalibrate the probe. There will also be a warning message that comes up on the screen indicating that we recommend, again, that you run the self-calibration routine. Okay, let's talk about handling IsoVu probe tips. So this is one of the, again, kind of common questions that I get into from a support perspective with this probe. So again, with any differential probe, it's important to keep in mind that probes in general have some of the highest use of any T&M piece of equipment, right? And I mean that from an extreme perspective, right? They get thrown into drawers, they get subjected to voltages and currents that are beyond their spec slightly. They get stressed from a flexibility perspective. And so IsoVu, again, from that regard, is no different. That being said, the performance and capability of IsoVu and its tips mean that the maintenance of those tips and the use of those tips is more important. So I thought I'd cover just a couple of things to keep in mind when using IsoVu's new tips. So what you'll see in the picture that I have here, this is again one of the newer 50x tips that we have for IsoVu Gen 2. And what I'm highlighting here is the structure and the mechanics of the tip itself are such like this, right? There's a box over here that houses the double EEPROM memory that is used to connect back to the scope and tell the scope what attenuation tip is attached and the propagation delay and things like that. And then there's a flexible cable that can be adjusted and bent within limits. But the important thing to keep in mind is the stress points when bending that cable ultimately put the most amount of strain mechanically on these 2 points. The point right back by this inflexible box or plastic shielding material, and then down at the probe connection point. In this case, we're using a square pin style connection or a wide square pin style connection. So there's a metal enclosure behind the heat shielding here. And in the case of like an MMCX tip, that would be a little bit further down the tip range. But the point here is when applying any particular force upon this tip, that's where the most of the strain will come in. And that's important because again, to achieve as high a performance in common mode rejection as IsoVu is capable of doing, we shield the entire cable with sort of a conductive metal mesh material all the way down from end to end on this tip. And that allows us to basically ground out any sort of EMI fields that may be coupling in around the measurement or around the probe tip and things of that nature. If those are damaged or if those are disrupted in any way, that can cause failure. So it's really important to kind of keep in mind that these tips are flexible, but they need to be taken care of and not just thrown into drawers and things like that. Now, some of the ways that I've kind of seen customers cleverly reduce the amount of stress on the probe tips are in two sorts of different ways. So one is there was a customer we worked with who had their test points kind of on an angle, and rather than try and position the probe and then flex the tip itself into the MMCX style connection, what they did is they actually hung the tripod for the generation 1 probe on the cage, or the high voltage enclosure around their device. And that allowed them to basically hang the probe tip up there and then connect at a perpendicular level into the board, or into the PCB board and the connection point. The other way that I've seen that done is kind of using gravity as your friend, where in the picture on the right, I've sort of drawn a diagram of what one customer has done, where they've taken the probe, they've fed it through the high voltage chamber, and basically hung it through some support clamps up on the probe head, and then they can move the probe head and probe tip vertically up and down into the MMCX test point. But it ensures that there's basically no strain horizontally on the probe tip or on the connection point itself. So that's really important to keep in mind, and some of the clever ways that I've seen, mechanical stress being reduced on the probe tips themselves. So speaking of tips, just a couple of other things to kind of keep in mind. We offer a variety of different tips for IsoVu. The main one that you'll see used most often, has arguably the best performance common mode rejection wise, is our MMCX style tip. MMCX is a shielded barrel style connection. It's relatively inexpensive. You can get surface mount connections on DigiKey and other vendors for less than $2. And it's for voltages, just under 250 volts or so. So, obviously, these are for planned test points in most cases. Since we don't live in a perfect world, obviously there are cases where there are unplanned test points that need to be added in. And we offer a couple of different videos and application notes that showcase how you can solder on MMCX surface mount and through-hole connections down onto a board in sort of an unplanned test portion. And we talk about some of the different best practices there, but the general premise, or the general summary when adding them to surface mount connections, is to keep the wires coming off of the surface mount surface mount MMCXs as short as possible. But again, the video kind of gets into more detail as to how to physically solder those down onto your board. So I'd encourage you to check out our website and find those kind of videos. We also offer a couple of different other types of connectors, including kind of your standard square pin and our wide square pin connections for the 2500 kV tips. There's adapters that can adapt from MMCX to square pin. That's this blue sort of barrel connection that you see here. And then there's also these tripod supports, which again, the goal there is to reduce any sort of horizontal stress that might be placed either on the probe tip or worse, on the connection point that maybe you've just soldered down to your PCB. And then it's also important to keep in mind that we also offer a variety of different other style tips that can adapt from either the MMCX or square pin standard or native tips on IsoVu. They include things like IC grabbers, banana jacks, alligator clamps, Y-lead to micro CKT type of connections. And those obviously can be used for either test points that are further away from each other, or to adapt into a connection point that's more in tune with what you already have on an existing board. So the general summary with this slide is to keep in mind that, of course, a shielded kind of solder-in type of connection like MMCX is usually preferred from a performance perspective, but we recognize that a variety of different applications require different test points, and so we have provided a variety of different leads and adapters to satisfy your needs. Okay, now other applications where IsoVu can be used. Well, this is the first one that we'll cover here is kind of where IsoVu has made a name for itself, and that's in wide bandgap material testing. So in this case, we're doing some dead time characterization, and the setup that I have here is we're measuring the VGS of some high side and low side FETs that are being used on a demo board, and we're comparing especially the high side VGS between IsoVu and kind of the traditional differential probe, our TMDPO200. So here you'll see in the blue trace, we've got low side VGS turning off in this case, or turning low, and our high side VGS is turning high. And then the green trace is our IsoVu, and our red trace is our traditional differential probe. And so you'll see, like you would expect, and what you've perhaps seen in other videos that we've done, the effects of the common mode voltage that is seen on this particular bus basically distort any sort of waveform or any sort of characterization capabilities that you may have on this high side waveform when looking at it through a traditional differential probe. On the other hand, IsoVu provides a very clean image of the exact signal that you would expect to see, perhaps the exact signal that you've simulated for. You can see characteristics like the Miller's plateau here are very apparent and are not shielded by all this extra ringing that's captured here. If we look at the low side, this is really where, I'm sorry, not the low side. If we look at the falling edge of the same pulse, you'll see this is, perhaps the more interesting or potentially troublesome part of this common mode issue, which is if you look at the red trace here, when the high side gate falls low, you'll see that there's enough apparent ringing here to actually turn back on the gate at the same time that the low side is turning on. And so that can, of course, cause shoot through and do all sorts of interesting magic smoke releasing type of issues with the FETs that you're using. And so at a bare minimum, you would have to adjust the gate time if you didn't know, where that ringing was coming from. So IsoVu, on the other hand, shows that there is some ringing that's indeed caused by the switch node, but it is not nearly as apparent as what the TMDPO200 sees, and so therefore is not as nearly as drastic and doesn't need to be included in terms of being able to optimize dead time. So that's, again, really where IsoVu strives and where it's made a name for itself. There's a couple of other applications where I've seen IsoVu do really well. One is on a power rail measurement where a customer was looking to discern what sort of effect common mode emissions in the environment that they were in were being coupled into the power rail. And so what you'll see here is channel 2, which is sort of the blue trace here, is using the traditional 10x passive probe of most oscilloscopes. And sure enough, there's a ton of ringing when there's a switching relay that's shown off screen here that's switching on and off and causing havoc when it comes to some of the ringing that you see here, whereas IsoVu basically doesn't show any of that. Again, being able to shield out and reject some of the common mode voltages that are apparent in the environment around the probe. Another potential application could be using IsoVu with high-speed serial applications. Again, in the presence of high common mode, low voltages in sort of the 1 to 2 to 5 volt range are really well suited for IsoVu. And so you can see one example where we're looking at a 40 megahertz clock here with 2 different probes, the top traces being from our TIVP and the bottom traces from our kind of traditional 1.5 gigahertz differential probe. You're seeing in a high common mode environment, there is indeed a lot more ringing or noise that you might see on the tops and bottoms of the traces. So, again, that's another potential area where if you're looking to validate where the ringing is coming from, IsoVu can help validate whether it is coming from a common mode source or not. And then finally, here's some other applications where IsoVu has been really well suited. Again, kind of in the same lines as what we were talking about earlier with the slides. Being able to make measurements in the presence of high common mode, whether that common mode is coming from switching relays or from one example where I've seen CT type of machines actually physically making measurements inside the CT machine. It really doesn't get any more EMI unfriendly than having to try to make measurements inside of there. And IsoVu does really well, again, from a rejection standpoint, being able to kind of peer through the common mode noise that's around the probe. Solar inverters, again, from a use case of solar inverters, automotive inverters, and motor drives, all kind of adopting this silicon carbide, gallium nitride type of topologies. IsoVu is very well suited for those types of applications as well. For those that are currently making floating measurements with scopes that are either ungrounded or are have the insulated tape around the grounding probe, right? We offer a safer measurement in being measuring capability and being able to use IsoVu to make those types of measurements through a galvanically isolated type of probing system instead of having to go the unsafe route. Systems where electrical stress is being subjected, right? So high surge, transient EMI compliance or debug type of applications. Again, the nature of being able to make those measurements and the wide dynamic range of IsoVu kind of lends itself to being able to be useful in those type of applications as well. And then one other one is, in cases where the measurement that's being made has to be or would desire to be further away from the scope. I'm thinking about automotive applications where measurements are being made inside of a dyno or are being made on a dyno inside of a chamber, and most of the connectivity options that are being fed to the scope are fed through a very tiny hole outside of the chamber. IsoVu would be really well suited for that for one reason, and that is we offer a 10-meter fiber optic cable option for IsoVu. So for those type of applications where you need to make some distance between the scope, the user, and the device under test, we offer that as well. All right, well, thank you very much. That concludes my part of the presentation. We are answering some questions through our chat interface, so we're welcome to stay online and continue to answer those questions. But if you have further questions about IsoVu, if you'd like to get a demonstration in front of you or perform an evaluation of the probe in your lab, we'd be welcome to come on site and help you with that. But I want to thank you again, and I hope you have a wonderful rest of your day.
Hi, and welcome to our double pulse demo. The focus of this demonstration is our wideband customers, and basically anybody who's implementing SiC or GaN in their devices or designs. Customers are preferring SiC and GaN or the wideband technologies, basically due to their higher efficiencies, their faster switching, and their smaller size. The key of what we're doing here is to provide a means for test, and the preferred means of test at this point is the double pulse test. To do this, we are using a small demo board here, which is basically representative of a small converter. So we've got a gate driver with a couple MOSFETs and an inductor to emulate the converter circuit. We're providing power to our demo board using the 2281S Keithley power supply. And then for the high voltage supply that would be normally on your output of your converter design is going to be supplied by our Keithley model 2470 source measure unit, which can go up to 1100 volts. On the very end, we have the measurement star of our show, which is our Tektronix MSO5 scope. So being able to take all of those great double pulse parameters that you're going to be looking for at the very end. And then really one of the key pieces for this is what drives the gate of these MOSFETs. as they're activating, right? So before I jump into what does that, is that we look at the purpose and the functionality of what the demo board is doing. So on the demo board, we have a gate driver, which is basically the insulator between your MOSFETs and some back driving circuitry. We have a couple SiC transistors that are being switched. Actually, one is being switched. We have a cascaded network of the two. The high side has its gate and its source shorted together, so it really doesn't have any activity itself, aside from on the off condition of the double pulse, where we use the freewheeling diode to be able to measure those parameters and characteristics of when the device is switched back on, because you're going to have some sort of transient activity. And we need to look at that for the power losses. The MOSFET that does get switched is the lower side MOSFET. And what we'll see is that during the testing itself, is that the first pulse, which is a longer pulse, which is used to charge up the inductor, will be a little bit longer. So we'll have it set for 10 microseconds over here. That allows us to do like the turn on and turn off parameters that we'll end up eventually measuring. I mentioned the turn off, that helps kick in the freewheeling diode. And then we turn the gate of the MOSFET back on one more time so that we can complete our evaluation of the turn on and turn off measurements. But we make sure that we keep that pulse very short in order to ensure that there's no device overheating. Now, you say, well, why do I have to have something like our AFG 31000? Well, it goes into time and effort. So you could have an engineer who wants to design their own pulsing type of circuit or mechanism. So it may be some FPGA device, but that takes time to develop. It's going to take time to test, and maybe you don't get it right. So instead of iterating over, we're providing you an all-in-one solution. So now that we have all of our signals applied, we can see the output of our circuit over here on the scope. The signals that we're monitoring are our VDS, which is the voltage drop across the drain and the source, which is actually what we're monitoring across the inductor itself, which is charging and discharging. On the second line here, we have our current that's going through that inductor. And on the third line, we're directly monitoring our gate to source voltage of the lower side MOSFET. Finally, down here on the final line, we just have a repeat of the AFG output, showing you the double pulse as it's coming directly from our source. One of the great things about this, aside from seeing all these great instruments from Tektronix in concert and working together to give you the full solution, what really puts the icing on the cake here is the measurements that we get through the scope. So normally what you would do in a setup to do the difficult method is you would use your cursors and you would dial into certain parts of, let's say, if you're looking at turn on time, you would set to 10% of your VGS, and then you would go over and look at, maybe 90% of a falling edge of one of your other drain to source voltage, and try and get that time on or that time off measurement. Instead of doing things by hand, the scope now has built-in software. So if I go to this measurement menu right here, and I go to the wideband double pulse test tab, I can see I have all these options for measuring. One of my favorites here is the timing. So we mentioned time delay on, time delay off, rise time, fall time. These are all important things for the customer. And we do them automatically. So I can set this up, I can add this to my arrays, and they show up all the way over here. You can't really see it on the right side of the scope, but we have this duplicated up here on this big monitor, and everything shows up and gives you everything automatically. So it really eases the process of making these measurements and getting you right to the answers that you were looking for.